Hello and welcome to this presentation of Self-Adaptation with Imperfect Monitoring. I am Mehran Alidoost Nia from University of Tehran. This is a joint work with my supervisors, Mehdi Kargahi from University of Tehran and Alessandro Abate from University of Oxford. Let me introduce myself. I am currently a PhD candidate in the RTEST lab at University of Tehran and working toward my PhD thesis entitled Runtime Probabilistic Analysis of Self-Adaptive Systems via Formal Approximation Techniques. I am also a program fellow at University of York and collaborating on Assuring Autonomy International Program as part of my PhD thesis. I give an overview on what I am presenting. Discuss about general self-adaptive system architecture and model-driven engineering. Then challenges of the research are presented and system model is expressed. After that, I introduce imperfect monitoring scenario as the main problem of the research and propose our solution to this problem. Finally, experimental results are discussed and the research is concluded. So let's start with some preliminaries about self-adaptive systems. A self-adaptive system consists of a closed loop that repeatedly monitors the local system and the environment. The local system is referred to the cyber part and the environment is the physical part of the cyber-physical system. A self-adaptive system is capable of adjusting the behavior of the local system against the changes imposed from the environment or some components of the local system. In response to those changes, the system issues some adaptation actions when the system violates what it is intended to do or a better performance be available. Self-adaptation equips the CPS with resiliency to runtime changes. Here we can see a high-level architecture for self-adaptive systems. As mentioned in the previous slide, the self-adaptive system consists of three main parts, include a local system, a control feedback loop, and the environment. As you can see in the figure, we refer to the environment as unmanaged component or uncontrollable resources. Local system interacts with the environment and is controlled by the MAPE loop. MAPE stands for monitoring, analyzing, planning, and executing. It is the basis for building a self-adaptive system that monitors the status of the local system and the environment, analyzes the collected data, decides if changes occur, plans what adaptation is needed, and finally executes the actions if need be. It can only affect on the local system or managed components. Here, as a case study, we have selected solar energy harvesting system for this research, mapping the main components of a self-adaptive system. Solar irradiation from the sun is the environment, and a set of sensors plus a solar battery panel are the local systems. The sensors work together and use the energy of the solar battery panel. The battery panel collects the required energy from the solar irradiation. The adapter adjusts the power mode of the sensors in order to balance between energy consumption and solar energy harvesting in a reliable manner. But cyber-physical systems must deal with fluctuations mainly from the environment. Self-adaptation is a need for cyber-physical systems to deal with changes. Based on MAPE loop architecture, model-driven approach is a good fit for self-adaptive systems. As the self-adaptive systems work in a dynamic environment, the model should be updated in each round of MAPE at runtime. We update the model with evaluation of its parameters. Due to the monitoring costs, if the model is not updated, the self-adaptive system possibly makes a wrong decision that has certain consequences, especially in safety-critical applications. In such situations that some parameters of the model could not be updated at runtime, there must be a solution to handle imperfect monitoring and decide about the current incomplete model of the system. Safety-critical applications need a reliable decision-making mechanism, even in the presence of facts. Model-driven approach is widely adopted by the community. In this approach, decisions are made with respect to the verification result of the models. In each monitoring step, the self-adaptive system updates the model, verifies it against some predefined properties, and if the verification result reveals that adaptation is required, adaptation actions are triggered. Model of the self-adaptive system is the combination of local system and environment. Here, properties aims at optimizing the behavior of the system against the changes. For example, in each round of make, we verify the system to find the actions that maximize the number of sensors working in high power mode. Model of the environment meets data-driven approach. This is where model-driven approach meets data-driven technique. As denoted in the figure, solar irradiance of the environment is indicated using hourly data. Based on the data, we extract the CDF of hourly solar irradiance. Using Pearson-Taki 3-point approximation technique, we discretize the continuous variable of energy harvesting to 3 points including 5%, median, and 95% quantiles. By doing that in 3 consequent steps, we can achieve a DTMC that proactively models the behavior of the environment. The model of the local system consists of 20 sensors and battery models. Each sensor works in 4 operating modes. The local system tends to maximize the number of sensors that work in higher power modes, and the battery tends to remain in regular level. Such intentions are brought to the model using utility functions. The energy consumption of the sensors is calculated based on their operating mode and is balanced with expected energy harvesting from the environment. So, let's define the main problem of the research. Imperfect monitoring scenario is referred to the situations that a part of monitoring data is missed. Assume a parametric MDP that represents the model of a self-adaptive system with a set of parameters V. If some parameters of V, namely delta, could not be updated, we say that the model is delta incomplete. The main problem of the research is to verify the delta incomplete model at runtime. Well, in this slide, we give our general solution to the problem. The general idea is to use pattern matching technique and match previous behavior of the system with the current one to estimate the missed parameters. We use a type of random walk, namely self-avoiding random walk, to model the behavior of the system. For each new run of the self-adaptive system, we generate a pattern 2. If some parameter is missed, we simulate the unknown step of random walk using the previous history of the system. We apply pattern theorem to match the current incomplete pattern with previous ones and to estimate the parameters. So let's have a brief review on the preliminaries of random walk. We use random walk in 2 dimensions, including the walk into 4 directions on x and y axis. Self-avoiding random walk is a type of random walk that limits the behavior of the walker or random process and avoids the walker to meet previously visited points. So, the self-avoiding random walk can generate unique patterns that can be matched using similarity measurement criteria. Well, we are going to dive into the proposed solution. We follow the solution through a simple example. As denoted in the figure, blue pattern belongs to the current run of the self-adaptive system, and the parameter of the model could not be updated in the 11th step. The self-adaptive system searches for previous runs in the history and finds a similar pattern, the black one, and matches it to the current pattern. Each walk has direction and weight of change. The direction indicates the possibility of change, and the weight of change estimates the valuation of the parameter. By matching the patterns, 11th walk of the current run is matched with the 13th walk of the history. So the weight and direction are estimated. As denoted in the result, positive x is selected. That expresses no changes occur, or the change is possibly negligible. So the self-adaptive system decides to consider no change and continues with the current strategy. The same procedure is applied for each missed parameter at runtime, and an estimation is calculated for that. So let's start investigating the experimental results. For the first step, we have verified the system once with perfect monitoring scenario. It means that there is no monitoring fault. The result confirms the validity of the methodology both in modeling and verification. As denoted in the figure, the chart compares the expected energy harvesting from the environment with the number of sensors working in high power mode. The system is allowed to increase the number of sensors working in high power mode proactively about 4 a.m. when the expected energy harvesting from the environment increases. Similarly, the system is forced to decrease the high power mode sensors about 5 p.m. when the expected energy harvesting from the environment decreases. As appeared in the experiment, our data-driven approach to solar energy harvesting helps out the system to estimate the expected energy harvesting through a look-ahead horizon in the next 2 hours. So, the system decreases or increases the number of sensors in high power mode in adverse. Well, we have designed 3 experiments for evaluating the correctness of the proposed solution. The first experiment regarding imperfect monitoring scenario is estimation of change at runtime. We have used self-avoiding random walk for generating pattern for each current run of the self-adaptive system. In 20 rounds of MAPE, each we have assumed that the monitoring process is imperfect, and for each step, as denoted in the figure, the change is estimated by matching the current pattern with the previous ones in the history. The result shows that the most of the estimations are correctly calculated, and the estimations are near to their real values. Apart from estimation of change, possibility of change is of interest that is almost correctly estimated in our experiments. Well, the second experiment is about analyzing the estimation error. According to the execution of more than 100 loops of MAVE, best, average, and worst case error in each round are denoted. As the worst case rarely happens, the average case is a good measurement for estimation error. Further, the distribution of error shows that the errors of estimation are mainly confined and bounded. We can see that the most of estimations have limited errors below 5%. In the third experiment on imperfect monitoring scenario, we have investigated the effect of estimation error on decision-making error. Surprisingly, we can see that the error in estimation is not necessarily led to wrong decision-making. It means that the self-adaptive system can make accurate decisions even in the presence of errors. The proposed system fulfills the accurate decision-making with accuracy of higher than 96%, while the average accuracy of estimations is lower than this value. Well, in this final slide, the highlights and achievements of the paper are presented. In this research, we tackled the problem of imperfect monitoring in self-adaptive systems. We have used a model-driven approach to engineering solar energy harvesting systems and elaborated a data-driven approach to verify the self-adaptive systems at runtime. We have proposed a decision-making approach that deals with imperfect monitoring scenario while the system model is incomplete, namely delta incomplete. The proposed solution includes a pattern matching system that matches the current imperfect pattern of the system with the history of the system using random walk. The results show that the accuracy of decisions are higher than 96% when monitoring is imperfect. The paper gives a certain solution to the problem of imperfect monitoring in self-adaptive systems and provides a pattern matching approach that its error is bounded. In this slide, you can see and follow the main references of the research that are categorized in 3 sections, including self-adaptive systems, solar energy harvesting systems, and related pattern matching techniques based on random walk. We have also released the source code of the work in GitHub. You can access it via the URL in the references. And with this, I'm done. I would like to thank you for your attention. Thanks again for watching.